And we are recording. So this is regarding exponential growth and decay. We have our foldable here. This is going to be the back that we will use to paste into our notebook at a future date. Basically, fold this to the middle. And then we're going to cut along the dashed lines. So we'll start out first with the upper left-hand corner, which is what is exponential growth or decay. So here we see an exponential function has the form a times b to the x. Neither a nor b can be 0. You have to have both of them. If b is a number bigger than 1, then you have a growth function. And if b is between 0 and 1, which basically means it's a fraction, then you have what's called decay. You can see from the graph here that it increases from left to right, so that's growth. On this one, it decreases from left to right, so that's decay. So you already get the idea of increase and decrease. Increasing function, growth. Decreasing function, decay. Okay, so an exponential model, we have two examples here. And while we use this f of x equals a times b to the x, for the purpose of these notes, we're going to change this b up just a little bit. So what we're going to use is y equals a, and instead of b, this time I'm going to write 1 plus r, where r stands for a rate, and all that's being raised to some power. A is still going to be your initial amount. R is going to be your percentage written as a decimal, and this X is going to be over time. So this first example says you buy a commemorative coin for $110. Each year, the value of the coin appreciates by 4%. Appreciation means going up. So this is going to be an example of growth. That's why we're using a plus here. Our initial amount is $110. For our rate, what we have is 4%, and 4% means 4 out of 100, but I need it as a decimal. So if you're not sure how to write it as a decimal, just do this division. 4 divided by 100 is 0.04. So now all we have to do is substitute these values into our formula. A is 110. R is 0.04 or 0.04, and we don't know what X is at the moment. We can simplify 1 plus 0.04 to be 1.04, and instead of using an X, since this is dealing with time, X is going to equal T, which is our time, so we're just going to use a T for it. And this is an example of growth. So when you get on the taking the EOC test, if you see this situation right here where it's adding, you know that you've got growth. All right? So now the next one is dealing with depreciation. Depreciation is when something loses value. So this is going to be a decay model. So we're still going to use something similar. Instead, this time of adding the rate, we need to subtract the rate. So we buy a stereo system for $780. Each year, the value of the stereo depreciates by 5%. So A is our initial value of $780. R is our depreciation rate, which is 5% or 5 per 100. Writing that as a decimal is 0.05. Now we substitute. A is our initial amount, so we put 780 in for that. R was our 5% written as a decimal, all raised to some power. We go ahead and do the subtraction here, so we are going to simplify. So we get 0.95, all raised to the, I'm going to go ahead and put the t here because remember x is equal to time, so we'll just let that equal to t. So this is an example of decay. We are going to use these two formulas for the next couple of examples. So here we have an exponential growth word problem. A town had a population of 2011. Then the population increased by 8% per year for the next 5 years. Write an exponential growth model for the town's population over the 5-year period. Use the model to find the population in 2014. So we're going to use P for our population, so that's like our Y or our f of x, and that's going to equal A times, and since we're increasing, are we going to do 1 plus? Yes, we are. So here we have all of our pieces. So now we have to identify what A equals. That's our initial amount. That initial population was 48,000. Our rate is 8%, which is 0.08 as a decimal. So when we and x is time, so we're going to have that equal t. So our population is going to end up as 48,000 times 1 plus 0.08, all raised to the t power. Simplify that. 1.08 in parentheses. So here's our model, but now we need to use this model to find out the population in 2014. From 2011 to 2014 is 3 years, so in this case t is going to equal 3. So we do P equals 48,000 times 1.08, all raised to the 3rd power, and then we just go straight to our calculator, to the regular screen, and we just type in what we have. Let's see, get where you can see this. There we go. Times 1.08, all raised to the 3rd power. And here's our population. Because this is dealing with people and we can't have a part of a person, we ignore the decimal. So our population becomes, after 3 years, 60,466 people. So that would be an example of a growth word problem. Our next word problem example is going to be decay. So let's see what we're talking about here. Between 2010 and 2014, the profits of a business decreased by approximately 0.5% each year. In 2010, the business's profit was 1.2 million. Write an exponential decay model showing the business's profit in year T. What was the profit in 2014? So again, we're going to say P equals, because we're dealing with profit, we're going to have A, and then this time, because it is decreasing, we're going to subtract that rate. So let's go over here and identify our A and our R. A is the 1.2 million, so that's 1,200,000. R is 0.5%, which is the same as 0.5 over 100. So now instead of 0.05, we have 0.005. And x is equal to time, so we're going to call that t. So let's start substituting. So for our profits, we're going to take our 1.2 million times 1 minus 0.005, because we had a 0.5%, not 5%. And we're going to raise that to however much time we have. Simplify. So we're going to get 0.995, all raised to the t power. So this is our model. And then they told us we want to find the profit in 2010. So from 2010 to 2014, t is going to equal 4 years. And this is all going to be taking place in the calculator after we get this written down. Do I have enough zeros? Yes. 0.995 raised to the 4th power. So we come back over here and we do 1.2 million. Times 0.995, all raised to the 4th power. And we are going to round this to hundredths because we're dealing with money. So this is going to end up with 40 cents. So our profit is going to be $1,176,179.40. And since this is money, we need to show that it is money. So they made less profit than they made in 2010, which is what we expected because their profits were decreasing. So your final answer should be smaller than the original answer. Okay, now we're going to look at 2 cases of graphing. So what we have here is f of x equals 2 times 3 raised to the x power, all subtracting 1. So we'll go ahead and go to y equals. We'll let the calculator do this work for us. 2 times 3 raised to the x power, and then I need to get out of the exponent and subtract 1. And look at the table of values. I am looking for the values for -1, 0, and 1. So for -1, I get -0.3333, so that's 0.3 repeating right there. For 0, I get a 1. And then for 1, I get a 5. So what that looks like in the middle here is the function evaluated when x is -1 is equal to 2 times 3 raised to the -1 power, and then subtract 1. For 0, it is the function evaluated at 0. So that's 2 times 3 raised to the 0 power, and then subtract 1. And then finally, we're going to change all of our x's to 1s because we are evaluating the function when x equals 1. So we get 2 times 3 to the 1st power, subtract 1. Now we need to graph these. I'm going to go ahead and graph the whole numbers first. At 0, I get 1. And at 1, I get 5. So over here at -1, we get a -0.3, which is basically 1/3, so that's something really close to 0. It's kind of small. So we have that right here. Now, with what we have done in the past, we said that our asymptote was always going to be y equals 0, that we would not cross the x-axis, and if it were not for this -1, we would have a situation where our asymptote would be 0. But because they took the whole function and moved it down 1, our asymptote has also moved. So it's now down here where y equals -1. So our asymptote is y equals -1. And that's because of this -1 right here. It moved the whole function down 1. So that means as we come over here to the left, as we're going that way, we're going to get really close to -1, but never equal it. And this other just goes off into infinity. So that is the graph of growth given this function here with our asymptote being moved down 1 unit. Okay, so let's look at an example of decay. Here we have g of x. We can see that b is definitely smaller than 1. It's a fraction, so that means we have decay. Let me fold this back a minute. Again, we're going to go to y equals and clear that out. So I have 4 times 1/2, 1/2 raised to the x power, and all of that, after we get that, we got to subtract 3. So now I'm going to look at the table of values and pull out -1, 0, and 1. So that -1 gives me a 5, 0 gives me a 1, and 1 gives me a negative 1. Now we just showed the substitution here in the middle, so g of x, when x is negative 1, that's g of negative 1. Replace that exponent with a negative 1. Everything else stays the same, just the x's are changing. We're actually putting numbers in for them so that we can evaluate. So finally, g of 1 is 4 times 1/2 raised to the first power, and then we're going to subtract 3 from that. So here we have our points. We can graph them. At negative 1, we get a positive 5. At 0, we get a positive 1. And at positive 1, we get a negative 1. Now, just like on the growth model, where it was subtracting 1, this one has us subtracting 3. So our asymptote has moved down 3 units, 1, 2, 3, and is now y equals negative 3. If this had been a plus, it would have moved up. So now we can go ahead and know that our decaying function is going to approach negative 3 as it moves out to the right and goes off to infinity as it approaches to the left. So our asymptote, we'll go ahead and write that in, is this line here, y equals negative 3. So that is growth and decay. Watch it again if you need to.